Okay, so we're now going to start problems from chapter 17. And problems from chapter 17, we're going to start with, actually, we're going to start with number 7, hoops. You know what, no, we're going to start with number 1. Number 1 says, Bernoulli, can we use probability models based on Bernoulli trials to investigate the following conditions or situations? And what we're going to do is we're going to talk about why these things can or cannot be classified as Bernoulli. And remembering that the 3 criteria for Bernoulli are, whoops, I got to start the timer. We're going to be 30 seconds off. So, criteria number 1 for Bernoulli is that you have to have success-failure conditions when it comes to your probability. Number 2 is that the probability has to be the same for every single trial. And number 3 is that your sample is going to be less than 10% of the population. So let's take a look at what the questions say here. Number 1, it says we roll 50 dice, or a die 50 times, if you think about it that way, to find the distribution of the number of spots on the faces. Is this Bernoulli? Well, do we have success failure? And right off the bat, the answer is no, we don't, because what we're doing is we're looking at the distribution of the 1s and 2s and 3s, 4s, 5s, and 6s, and that's not success failure, it's not Bernoulli. Bang, we're done. 2, how likely is it that in a group of 120, the majority may have type A blood, given that type A blood is found in 43% of the population? So do we have success failure? Yes, it's either type A blood or it's not. Is the probability the same? Is this person likely to have, or the probability of having type A blood the same as the next person? Yes, as long as they're not related. And is our sample less than 10%? Well, our sample is 120. And if it wasn't less than 10%, then that means that the maximum population would be 1,200, which means that we, people as a species, are endangered. And that's certainly not the case. So yep. Okay, we're good. All right, 3, we deal 5 cards from a deck and get all hearts. How likely is that? Do we have success failure? Either you get hearts or you don't. Oh, by the way, we're on page 398. So either you get a heart or you don't. Is the probability the same? Well, when it says we deal 5 cards, the implication from this is that I'm dealing a card and another card without replacement. So the probability is not the same. It's not Bernoulli. We wish to predict the outcome of a vote of school budget and poll 500 of the 3,000 likely voters to see how many favor the proposed budget. Okay, so do we have success failure? Yeah, either you're in favor of the budget or you're not. Is the probability going to be the same? Yeah, probably, because just like with blood, the probability that this person is in favor of the budget is probably not going to affect the probability that the next person is in favor of the budget, unless, of course, they're related, or, you know, they're spousal units or significant others, because, you know, the joke is, and the statement is, oh, opposites attract, but in reality, opposites divorce. So if you honestly have a different political opinion than your significant other, chances are you're not going to stay together that long. So is the probability the same? Is this person's decision on vote going to affect that person's decision on vote? Probably not. And is our sample less than 10% of the population? Well, we're talking about 500 out of 3,000. That would need to be less than 1/10, but we're looking at 1/6. So that's not the case. We are not Bernoulli. E, a company realizes that about 10% of its packages are not being sealed properly in a case of 24. Is it likely that more than 3% are unsealed? So is it unlikely that 3 or more are unsealed? Is it success failure? Either it's sealed or it's not. Yes, underneath the case. Is the probability the same? Is the probability that this product is going to be unsealed going to affect that one? And the answer is probably not, because you're thinking that you have a large population of products and they should get randomly assigned to a case, and that's fine. So that probably is not the same. Is our sample less than 10%? Now, let's be careful, because our sample is not 3 out of a population of 24. Our sample is actually that 24 or 1 case. And we have to ask ourselves, is that less than 10% of all products that this company is going to make? And realistically, that means if it's not, then at maximum they're going to have 10 cases or 240 products. And is that company going to survive if they only have 240 products? Probably not. So we're probably okay there. So we are Bernoulli on through all three criteria. So we are Bernoulli. Okay, moving on. Number 7, hoops. A basketball player has made 80% of his foul shots during the season. Assuming the shots are independent, find the probability that in tonight's game he A, misses for the first time on his 5th attempt. Okay, so this is what I know. I know probability for success, we'll call it P, is equal to 0.8. And the question says, what's the probability that he misses for the first time on his 5th attempt? So we ask ourselves, first off, what kind of probability is this is geometric, because you're going to keep going until you get your one thing that you're looking for. Here we're going to keep going until we get our first miss. So, but again, I'm going to ask myself, because I could think about the formula for geometric probability, which is 1 minus p to the n minus 1 times p. But that is more than I really need to know, because all I need to think about is, what's happening? How many events do I have? I have 5 shots. And what happens on the first one? The first one, he makes it, so he has success. What happens on the second one? He makes it, he has success. What happens on the third one? He makes it, he has success. What happens on the fourth one? He makes it, he has success. What happens on the 5th one? He fails. So I figure out these probabilities. Success is 0.8. These shots should be independent. I've got 1, 2, 3, 4, 0.8 to the 4th power. 0.8 times 0.8 times 0.8 times 0.8 is going to be 0.8 to the 4th power. Times failure, the complement of success, which is going to be 0.2. So it's 0.8 to the 4th power times 0.2. Break out Mr. Calculator. And we'll say 0.8 to the 4th power times 0.2 equals 0.08192. To 4 decimal places, it'd be 0.0819 equals 0.0819. Geometric probability is really easy. You don't need to know the formula. All you need to sit there and think, what's happening? All right, B says, makes his first basket on the 4th shot. So I ask myself, how many shots do I have? 4. He's going to keep going until he makes his first shot on the 4th one. It's geometric probability again, but again, I'm not going to worry about the formula. I'm going to say to myself, he makes his first basket on his 4th shot. So what happens on the first one? Failure. What happens on the second one? Failure. What happens on the third one? Failure. What happens on the 4th one? Success. Failure, failure, failure. 0.2. To the what power? To the 3rd. Times success. 0.8. 0.2 times 0.2 times 0.2 times 0.8. Let's find out. 0.2 to the 3rd times 0.8 equals 0.0064. Woohoo! That was pretty easy. All right. Number C. Yes, it is a number. Makes his first basket on one of his first 3 shots. Okay, I need more space here. So what I could do is this. He could make it on his first shot, which means I would have success, and that would be 0.8. He could make his first basket on his second shot, which means what I have is I have a miss, and then I have success, which is 0.2 times 0.8, which is going to be 0.16. He could make it on his 3rd shot, which means I've got failure, and then success. 0.2 times 0.2 times 0.8 is 0.032. And it could be this, or this, or this. And or means add. So I add these together and I get 0.992. Actually not hard to do. But then I could ask this question and say, what I'm really kind of asking here is, what's the probability that he's going to make a shot on at least one of these? Now think about what we said before, is that at least one is the complement of none. So if I find none, which is failure and failure and failure, which is 0.2 times 0.2 times 0.2, or 0.2 to the 3rd power, that's 0.008. Are these complements of each other? Yeah, they are. So what I actually have is 1 minus all failures, which would be 1 minus none, which would be at least 1, and I get this answer. So I could think about that as being at least 1, and find it by finding the complement of the none, which is actually a little bit easier. Okay, so we'll be back right after the break because I went too far anyhow.